Hello everyone, welcome back to Geology 106, and today we are going to be talking about sedimentary rocks, and we are also going to be talking about metamorphic rocks today. This is one of my favorite metamorphic rocks that the college has. So welcome. Set this guy down. All right, metamorphic rocks are really heavy. They are so heavy. At least normally they are. So we are going to be starting at 3 o'clock. The time right now is 2:52. So if you are watching this later, you can fast forward 8 minutes into the video if you want to get started right away. So how are we all doing today? I myself have been extraordinarily busy. It's been one of those mornings that's been like a go morning in terms of work. I know I'm working from home, but still have many things juggling regardless. Awake-ish. I feel that. Awake-ish. Yeah. But I'm only semi-awake. I still need to have more of my tea before I probably feel a bit more awake. I think I'll be fairly tired this evening because, like I said, haven't really stopped since I started this morning. So it looks like we have a few more people. How y'all doing today? How's today going? I'm so excited to look at rocks today, by the way, guys. I'm really excited. The PowerPoint leaves some to be desired from me anyways. It's not my favorite PowerPoint. But regardless, I'm so excited to look at rocks today. Noah's good. Genesis did some errands. That's awesome. I actually went grocery shopping yesterday, guys. It was great to get out of the house. I haven't been grocery shopping in over a week. I don't think I've really gone. No, my husband and I stopped by his folks' place to pick up some yard tools that they were loaning us. But aside from that, I have not been out in the world. So yeah, doing some errands is always nice. It's nice actually getting out there these days. Let's see, it is 2:55, so we will begin in 5 minutes. Yeah, it has been fairly nice out today. Yesterday was so hit or miss, and then Monday I was filming some physics experiments for another class, and it was really windy, and I had to contact the professor, and I was like, I don't know if this is going to work because I have to film outside to eliminate motion blur, but it's really windy, and that affects the motion of the objects. Yeah, so it's been fairly nice, mild weather today. What is this out you speak of? Yeah, I know, outside, the out world, right? Oh gosh. It's definitely been one of those interesting times where it's like, I think I saw a meme that said, politics aside, I thought it was hilarious anyways. It said, I can't wait till they legalize outside again. Oh my gosh, that got me for about a minute. So yeah, Echo's been outside, just hasn't left her farm. Living on a farm sounds really nice right now. I don't know why, but just, yeah. I kind of grew up a little bit more rural and Snohomish in kind of the Clearview area. So I've always been more of a, I like to be a little bit further out from the city. But my husband works normally in Seattle. So I can't live that far away from the city of Seattle without imposing extraordinarily long commute times on my spouse, and that's just not fun for either of us. But yeah, so living on a farm. Have you always lived on a farm, Echo? Yep. Farms are awesome. I wouldn't actually know though, because I have not lived on one. Just lived a bit more rurally. So looks like we've got about 4 people today. Who's excited to look at rocks today? Anybody? I know that for some people, rocks are like, take it or leave it, You brought the farm with you when you moved out. Yeah, excited to look at rocks. I got some samples today that hopefully will be really interesting and exciting for you guys to look at. I don't know. I know that I'm fond of these rocks that I grabbed. Genesis found some rocks that she collected today. Awesome. I have too many rocks that I have collected, so I will not be participating with you guys on this portion of going out and finding 3 rocks and bringing them home and photographing them because I have too many already. Never help a geologist move. You'll just be carrying boxes of rocks. Literally, when I moved to last, I had some boxes that were labeled like living room rocks, some that were labeled like fragile rocks, and others that were labeled nice rocks for some reason, not like the type of nice GNISS that we'll be looking at today, but like actually just NISE, nice rocks. Like these are the good ones. These are the ones you display. So, and it is almost time to start rock triage. I'm not sure I know what you mean. Or triage. I'll have to ask for clarification on that one. Yeah, you guys can't see, but next to me, you can kind of see that there's a shelf here, and it's almost completely rocks. And it's not the only bookcase in this house. There's one other shelf that is a bit smaller. It's also completely rocks. And there are many unopened boxes still in the garage. Like medical triage. Let's see. When you have to pick and choose something. Yeah. Oh, story of my life. Because like I have the geology like rock collection buzz pretty bad. I kind of had a reputation for it amongst my classmates, even in my program for geology. And like, what the hell is this kid doing? She's always grabbing rocks and stuffing them in her backpack out on these field excursions. And I'm like, I really want to teach someday. And I don't know if where I teach, whether that'll like what level that'll be, and if I'm going to teach somewhere that already has a rock collection or has none. So I was always like collecting and hoarding these rocks because I was like, I'm set on teaching someday. And I don't know if wherever I go to teach geology will have a collection because I could teach at a high school or college or something. So I was always hoarding rocks, justifying it that they were going to be my teaching sample collection someday. And now I actually do use them. Not all of them, though. All right, so it is now 3:01. Looks like we've got several of you guys here with us. So let's go ahead and get started. We are going to be covering an awful lot today, trying to squeeze both sedimentary rocks and metamorphic rocks into the same lecture. Quite a task to try and squeeze two rock types into one lecture, especially if I'm trying to keep that lecture to like an hour and a half of time, to try and keep you guys from getting too fatigued. Let me pull up here my slides. I wasn't able to print out the lecture again today for you guys. Bummer. The printer is in the room that my husband uses for his home office. And he was in meetings most of the day. So that became, we need to move the printer is what that means, to a more accessible for both of us location. All right, let's go ahead then. So I have added to the lecture link that I posted for you guys on Canvas earlier this week. So if you would like to access this week's PowerPoint, today's PowerPoint slides, they are again on Canvas. It's that same link that was there Monday. I just added a bunch of slides to it just now for you guys to view. And we're going to be picking up on slide 20. Let's see, I see at least a couple of you guys on there. Would love to see a few more smiling faces over there on the Google PowerPoint. That'd be awesome. Just so I know you guys are with me. There's a meme there. It's great. A student sent that meme to me and it was glorious. It says that Dwayne "The Rock" Johnson refuses to confirm whether he's sedimentary, igneous, or metamorphic, which of the three rocks, and it says that he has angered geology fans by refusing to confirm. That may have gotten circulated after it came to me. So let's go ahead then, talking about sedimentary rocks. So what is a sedimentary rock? First, we should mention that we talked about igneous rocks already, and igneous rocks are those that solidify directly from a liquid. So you have liquid lava or magma, and when that hardens and solidifies, the rock that is created from that is of the classification igneous. And it can be either an intrusive igneous rock and having these nice large crystals, or it can be an extrusive igneous rock, solidifying outside the earth on the earth's surface, and it does not have usually any or maybe just a few visible distinguishable crystals in it. So let's talk about the next type of a rock. The next type of rock that we're going to be talking about anyways is sedimentary. And how do you make a sedimentary rock? What defines a sedimentary rock? We defined igneous. Well, in order to make a sedimentary rock, you first have to break down material, either former rocks, or sometimes it's breaking down shells. Sometimes breaking that rock or those shells takes place in the form of physically, mechanically breaking those rocks down, via one of the mechanical weathering agents that we talked about last time, where you actually just break something down into smaller bits by like smashing it or etc. Another way that you can break down a rock is also by dissolving it. And when you dissolve something, you're literally doing stuff on a chemical. We're talking about things on a chemistry level here, but we're dissolving ions. into a solution. And then the next thing from there that you need is you need to transport what you've just broken down, whether it's because you dissolved it or you physically broke it down into smaller bits. And that's what the next slide there is about, that says sedimentary rocks, creating sedimentary rock part 2. And you see there a bunch of water, muddy water, and you see this cliff, kind of this embankment in the background there that's all dirty. There's some grass up on top, and then there's just this drop off into the water, and it's all like mud and dirt. And then you see a bunch of, really murky, dirty water. That's the water there is transporting the sediment to another location. There's also a picture there of a bunch of wind blowing across a farm and picking up a lot of the dust and dirt particles that used to be a rock and blowing them away into another location. So first, we need to break something down. Second, we need to transport it. We got to move it. Third, the material that you are transporting needs to be deposited, and that's the next slide there. You're looking at 3 different kind of depositional environments depicted on that slide. The first one in the top corner there is what's called a soda straw, and that is in a cave, actually. What's happening is that there's water in these caves, and that water carries those dissolved ions from, maybe another rock that got dissolved. It's carrying those, and then that water will sometimes, as it moves through areas or across various surfaces, it will leave behind some of that load that it's transporting, right? And it will deposit. Deposit literally means, setting something down. You probably can't see because I set that down on my laptop, but, transportation, deposition, deposited it right there. So the other depositional environments that we're looking at there is, one is a dried up river channel, specifically in Arroyo. It's kind of a smaller arroyo, but nonetheless, it's just a dried up river channel. And we see a bunch of cobbles and dirt, and bits of rock that have been deposited in that dried river channel by water that was rushing through there, and then left behind some sediments and pieces of rock. Sediment is just small ground up rock, by the way, just to make that distinction there. The third picture that we're looking at there is a swamp. What we're seeing is this water that is very anoxic, doesn't get a lot of movement, and there's all this organic material that's falling into that swamp. You can make a rock out of organic material rather than breaking down an igneous or metamorphic or yet another sedimentary rock. And we'll get more into that. So after depositing, you then need to, going to the next slide, slide 24, we're going to talk about lithification. So next, the final step, the fourth step, is you need to lithify your material. Lithify is a fancy word for turn to stone. So now that we've got our material that we broke down, we transported, we deposited it, now we're going to turn it to stone. Lithification. How does that happen? It happens by a process called, how do I want to say this? The most effective way to say this. To lithify a sedimentary rock, what you're looking at is compacting that material, right? So you're going to apply pressure to it, and that's kind of what that top corner photograph there is depicting. You're seeing that material being squished together, and then right below it you see a photograph of these yellow grains of rock or mineral, and there's this kind of white-like stuff in between the grains, kind of connecting the grains. That is like cement, natural mineral cement that has grown in between the clasts of that material and binds it together. So you compact it, you also introduce some maybe water that is carrying some dissolved ions in it, that when that stuff gets solidified, it literally binds everything together. So, and it's usually a mineral that gets precipitated out or something like that, that cements everything together. There is one other way. Cementation is, I don't know if I want to call it one other way, but another way that you can lithify something in addition to just this process of compacting and cementing things together is you can literally just precipitate a rock out of solution. So think of that cementing material, but the whole thing is that cemented material. That's what you're looking at in that bottom corner right above where it says copyright 2017 Pearson Education. There's this, what that is there's like this branch, this tree branch that is fallen over and is on the banks, on the shore, at least I'm pretty sure it's a tree branch, is but coated with a bunch of, looks like probably salt, maybe gypsum or something. And it's literally just dissolved out of this really salty water and precipitated onto this tree branch and completely coated it and crusted it. So you can have an entire sedimentary rock that just completely precipitates out of solution. And thinking that kind of the cement-like material. Let's see, I see some comments. Noah has commented about how like mud and sand, such as coal, we will be talking about coal in this lecture too. So I also had a student named Cole once, and we talked about coal in that class, and that lecture day got a little confusing, just a little bit. So let's move on to slide 28 there. There are a few different types of sedimentary rocks. And we're going to be looking at a few examples of each and highlighting just a few examples. So we've got clastic sedimentary rocks. We also have biochemical sedimentary rocks, as well as organic and chemical. So let's examine that first category there and talk about clastic sedimentary rocks. So clastic sedimentary rocks are going to be they're characterized and defined based on the sorting of the material in that rock, as well as how angular or spherical the material is in that rock. So looking at slide 29, you'll see in the top left corner there a few kind of circles that have a bunch of different material in them, and some of them are, say, very poorly sorted. And in that bubble, what you're seeing is some of those grains that are in there are really, really big. And some of them are like teeny, teeny, tiny, right? That's poorly sorted. It's not uniform in size. What we're looking at is kind of uniformity of size when we talk about sorting. So you can kind of see the scale there going all the way to very well sorted. And in that bubble, you see a bunch of grains and they're all about the same size. So we would call something that has grains that are all about the same size to be very well sorted. So let's go ahead and take a look to, I don't really actually have samples on me that kind of show that spectrum of really well sorted versus poorly sorted. But if you look at the rock on slide 29 in the top right corner, you'll see a sample that's pretty well sorted. I wouldn't say it's very well sorted, but it's definitely well sorted, where all the clasts in there, all the kind of dark gray dots, which are smaller bits of rocks in this example, they all happen to be relatively close in size to one another. Whereas that rock in the bottom left corner, you have some chunks in there that are like really, really big and some that are really, really tiny. That is definitely poorly sorted. So we also classify clastic rocks not just based on their sorting, but also how angular are the clasts that form up that rock versus how spherical are those clasts. So hopefully you guys can see that in the slide on the top. All the clasts that make up that rock are pretty well rounded. And then in the bottom, you see that everything is pretty angular, right? So let's take a look at that. I have some samples here showing the distinction between the two. All right. I've got the slides pulled up. So let me pull back over to the YouTube lecture here so that I can see how well this is showing up on here. So hopefully you can see in here that these clasts that make up this rock are mostly rounded. Oh, you can see it really well on that side. Pretty round. This guy here is fairly round. This guy here is like kind of long in shape, but it's still, all the edges are pretty rounded. They're not really jagged or angular, right? So even though it's kind of got a long shape to it, it's not pointy at any, it's not really very pointy. Same on that surface right here. And you can see all the bits that make up this rock have been rounded out. No sharp, well, there's a couple, but mostly no sharp angles on that rock. Let's see, is that caused by the time each piece of sediment has weathered? Yes, absolutely right there. So with a clastic sedimentary rock, essentially what a clastic sedimentary rock is that we have a bunch of smaller bits and pieces of specifically of like rock, other bits and pieces of rock or mineral that have been compacted and cemented together. And we're not really talking so much about precipitation. We're not really talking a ton about organic material, right? They're largely the compacted and cemented bits and pieces of other rocks. So this rock is made up of like a ton of different chunks. Like you've got one right there, another one there, another one here, there. And there's a bunch of cementing material in between. And the reason why the clasts in this guy are so much more angular than the clasts in this one is because the bits and pieces that make up this rock, they traveled either a greater distance or for a longer time. And because they were transported so much farther, they were rounded out in their journey. Because think of it like as being in like a rock tumbler, if you guys know what a rock tumbler is. This guy was tumbling along for so long that as the pieces tumble together, they sort of bump into one another and round each other out and break off those sharp angles, any sharp points that may have been on the clasts, right? And they round each other out as they continue being transported. So the clasts in this rock, let's see if I can kind of get them to show up nicely. The clasts in this rock were all angular at some point. Yes, indeed. It's just that the clasts traveled such a great distance and have been through so much that they've gotten rounded out over time. Versus the clasts in this rock, right, which are largely far more angular than the other one. And as a result, since this one just the clasts didn't go very far before they got compacted and cemented together. So this rock here, we would call this a conglomerate because it has rounded bits and bobs in it. And this guy we would call a breccia because it has angular bits and bobs in it. Bits of sedimentary rock. Let's take a look at another type of sedimentary rock. Put these guys back in the box on my floor. Let's take a look at sandstone. So in the slide there, slide 30, the sandstone pictures that I have on there, they're mostly this kind of brownish, orangish, reddish color. Sandstone is not always brownish, orangish, or reddish in color. It can come in all kinds of colors. And there are several types of sandstone. There's quartz sandstone, meaning that the grains that were cemented together are largely quartz grains, right? And Arcos means that greater than 25% of the things that are cemented together are feldspars as opposed to quartz crystals. They're feldspar crystals. Again, looking in your mineral kits here. Sorry, I lost my sheet that told me which numbers were your guys' samples, but you have like a quartz sample in your kit, right? Versus feldspar sample in your kit, right? So quartz sandstone is just really, really tiny grains of this. Lots of small grains of quartz, more than 95%. And then an Arcos sandstone has at least 25% of the material is feldspar crystals. And sandstones are definitely characterized by having kind of a sandy feel to them and a sandy look to them as well. And I have a few sandstones here that I will show you guys. Let me locate them all. You have some in your kit as well. I forgot to find the numbers for you guys. You guys did receive a key though with your kits, correct? Can you let me know in the messages there if you did indeed receive a key, an answer key to which samples are which in your rock kit? So here, if you have the larger rock kit, you're going to be looking at samples 25 and 24 are both sandstones. Yep, yes. Okay, good. So you guys know which numbers then are the ones that are sandstones in your kits. So got some sandstone there for you guys to look at. Let's take a look at some bigger samples of sandstone though. I love looking at rocks. So here's a sandstone that I collected in either Utah or Arizona. Not quite so sure. I'm sorry, my nail polish is like all over the place. It's been on the back burner lately. I wonder if I can, how close I can get this to maybe show you guys kind of that sandy texture. Not so well. Can you guys, like in the sample that's in your kit, the Arcos, and I think you guys also have like a quartz sandstone. When you feel them in your hands, do they feel really sandy to you guys? Can you feel that kind of granular texture? Sometimes the sample key is vague. It is. I will do my best to like walk you guys through that as much as I can. You pull up that sample key here too, just so I have it on hand. I don't like the sample key that much. Of course, what rock kit is going to be perfect though, unless like I put it together and then it meets whatever specific standards I personally have, you know, such as life. So yeah, you guys know your number 19 is a sandstone and number 21 is an Arcos, which just means that it's also a sandstone, but it's got a lot more feldspar grains in it. And I'm guessing that your 19 sandstone is a traditional quartz sandstone. I have another sandstone here. Bought this guy at a rock shop in Vantage, Washington. I believe it's Vantage, Washington. Getting kind of some blue colors here on my, turns the screen, the white balance kind of blue when I bring this guy up or bring it too close. But in any case, very lovely. And Here we can see some of the sedimentary structure that is a result of the sand as it was being deposited and whatnot on the back of this. Can you guys see this really faint line that is down on the side there? That's where the rock saw cut this slab. Because you have to cut this guy just right to kind of see, I think, what you're going to want to see out of it. So it's one of my favorite pieces of sandstone. It almost looks like rolling hills or a piece of art. All right, enough of that. Let's talk about more rocks. Yes, very faint, but it's there. Let's talk about another type of clastic sedimentary rock. Let's actually talk about 3 other types of clastic sedimentary rocks all in one slide. Slide 31 there. We're going to talk about siltstone, shale, and claystone. Claystone is also sometimes called kaolinite. So siltstone, shale, and claystone are all fairly similar. However, what defines the difference there is the size of the particles that make up this rock. In all 3 cases, first with conglomerate and as well as breccia, we had larger, very visible clasts. In sandstone, we got into some kind of sand-sized particles. Now we're going to talk about siltstone, shale, and claystone, and these classed sizes, the particles that make up this rock, are even smaller. So siltstone, shale, and claystone. With siltstone, the particles are what we call silt-sized. So the material that makes it up is pretty small. Likewise with shale and claystone, but claystone is reserved for only the finest of particle sizes. So we're talking like dust that's been compacted and cemented together. It's very powdery, and when you feel it, I don't think you guys, double check, you don't have claystone in there. If you did, it would just make a mess, because I'll show you. Hopefully it shows up on my screen. Let's take a look here. Let's take a look at claystone or siltstone. So here I have a nice gray claystone. It is so soft. It's still hard. Can you guys hear that? But it's still hard, and it's still a rock, but it's so soft and just dusty because its particles are so fine, right? Now I have dust all over my hands. That's okay. I'm a geologist. I kind of live for that anyways. So go ahead and grab your sample number 20 out of your kits, because that one is shale, right? And let's talk about the difference between siltstone and shale. I grab my shale here that I've got, as well as my siltstone. So siltstone, I hate the word siltstone. I really prefer the term mudstone personally. So mudstone, I've got a nice sample that I found here at the college. Quite envious, this guy. It breaks into these kind of blocks. And that's really indicative of the fact that what you are holding is either that mudstone, or also known as siltstone. Strong preference for the name mudstone. However, shale, on the other hand, let me see. Hopefully yours looks something like this guy right here in your kits, your number 20. You can really see what I'm trying to get you to see very nicely right here. These lines there. Shale, on the other hand, is very platy. And it really breaks into like sheets instead of this kind of like blocky texture. So this one, I'll show this one up a little bit closer. So there's actually a fossil, an imprint fossil on this one. I don't know if it will show up though, because it's just barely on the surface there. You can see kind of a leaf. There's also some dendritic texture, pyrolusite mineral on there. Y'all can look that up in your spare time if you're curious about what the heck pyrolusite is. It's a mineral. That's not the leaf there. But there is like a kind of a leaf on this surface. It's just so faint. However, what I want you guys to see is how this has broken off into like sheets. It's we call that fissile, like a fissile texture. You can kind of see how it's breaking off into sheets there. Versus, again, this kind of blocky fracture, not fracture like crystal fracture, but just the way that this is breaking off. And we looked at the siltstone. I don't want to pick that up again. Gets all over my hands. I'll be picking up more messy rocks here in just a minute, though. So that kind of wraps up talking about the clastic sedimentary rocks that we're going to be chatting about. So let's go ahead then and start changing gears over from clastic sedimentary rocks over to biochemical sedimentary rocks. So what is a biochemical sedimentary rock? A biochemical sedimentary rock is when you cement together the shells of animals. So there is a particular sample that I'm a fan of called coquina. I've heard it pronounced a variety of ways. I believe coquina is the way that I've heard it pronounced the most. A lot of so there's biochemical limestone, right? There's fossiliferous limestone and chalk are examples of biochemical limestones. Diatomite, we won't be covering diatomite, and also coquina. Let me grab a sample of the coquina that I have. So this one's been through it. There are better samples on campus, but I was in a big hurry when I went there because I was trying to get on and off campus as quickly as possible with this pandemic going around. This is kind of an example of a coquina, not the best sample I've ever seen, not the most exemplary sample. But you can see that it's a bunch of shells that have been smushed together and cemented together to form a rock. I have another biochemical rock here. This one, I don't know that this one qualifies as a coquina. This might just be more of a fossiliferous limestone here. But all of these like lighter colored swirls in here are fossil shells, Turritella to be specific. I'll type that in the chat and y'all can check that out on your own time. I wonder if I even spelled that right. I didn't even spell it right. Whatever. Turritella, I can't spell. I'm dyslexic, mildly. I just like to use it as an excuse. I'm mildly dyslexic. So you can see one such shell right here on the edge there, a little spiral shell there, a little Turritella guy. And then all of these are just the cross sections of a bunch of them. There's kind of a whole one right there that got cut in half, lengthwise. Some of these are the cross sections of them. Enough of looking at that sample. But yeah, basically biochemical. You've got a bunch of shell material that was cemented together. Fossilized coral also looks like this. I have like this most magnificent fossilized coral specimen. I couldn't find it for a lecture today. I'm wondering if it's in my garage or something, but I have one that's like this big. And thank you, Audrey Huerta, Dr. Huerta, who helped me backpack that one out of the field. It has like a few different kinds of coral on it. My backpack was already full of other fossil samples, so I couldn't fit it into mine. And so Dr. Huerta backpacked it out for me. Let's see, where's another fossil limestone I want to show you guys? Right here. This guy came from that same location I was just talking about. This is a smaller sample. So right here is a fossil coral. So this came out of Idaho, near Mackay, Idaho. In case y'all are curious, when I go there, I keep saying y'all a lot today. Here's another fossiliferous limestone. There's the coral right there. I believe I showed you guys this last time. And this one kind of has also like a conglomerate type aspect to it, where you can see different like bits of rocks of limestone got cemented together there. So let's go ahead and move on to slide 33 and chat about, let's see, is there anything I really want to say about fossiliferous limestone? Not much. I kind of just said everything there. You can see some of the fossil coral there on the bottom two pictures for slide 33. Again, it's just this fossilized plant, or not plant, excuse me, like shell remains of an animal, not a plant, animal. We're talking animals here. So let's go ahead then and go to slide 34 and talk about two other kinds of biochemical sedimentary rocks. We'll talk about chalk and biochemical chert, excuse me. So chalk is another type of limestone. Yes, chalk, the chalk that we used to write on chalkboards with, is typically actually made out of a fine-grained limestone, a calcareous, that was formed from calcareous plankton shells. So we're talking plankton, and they have shells that are calcareous, very calcium-rich shells. Lots of calcium in their shells, just like in our bones, right? And those will also fizz with the, if you happen to have any hydrochloric acid. If you put hydrochloric acid on the calcareous shells that make up like chalk limestone or just regular fossiliferous limestone, you're going to see it fizz because they're calcareous. It typically forms like an ooze on the bottom of the ocean too. It's kind of gross. And then we'll also talk about biochemical chert. So these are very similar. Biochemical chert is very similar to chalk, except instead of being formed from calcareous plankton shells, biochemical chert is formed from a different type of plankton shells that are primarily made out of silicon. They're made mostly silicious, right? We don't have a lot of calcium in there. It's mostly silicon. Think glass. So as opposed to like our bones, which are more calcium-rich bones. And as a result, they don't fizz. Biochemical chert does not fizz when you put hydrochloric acid out of it. It's just a different type of plankton. Do I have some chert here to show you guys? I do. And I also have some chalk. Actually, this one's a diatomite. This is diatomite. It looks just like chalk, except it doesn't fizz. Or is this one the diatomite? It's so hard to tell. You really have to do the hydrochloric acid test to tell. Let's find out. Nope. I was right the first time, I think. So, chalk weighs nothing, right? Just like a regular piece of chalk. So even though it's gigantic, it literally doesn't weigh anything. Transportation right there. Could you guys see that? Transportation of sediments. And then here I have a piece of chert. Click over so I can see what you guys are seeing. If you guys notice, the surface texture of these is so extremely different. This one's chalky and powdery. This guy is not chalky or powdery at all. And it's heavy. Very heavy. So I won't drop it on my computer, I promise. But you can see it's got a very smooth surface. And even where it is fractured and cracked, it kind of has this really interesting texture to it. Let's see. You can find stromatolites in chert. I didn't realize that they would be in chert as opposed to in like more of like a limestone. Wonder if can it be both? Well, it would imply then that stromatolites are just a more siliceous material as opposed to like calcareous material. Thanks, Noah. I didn't know that stromatolites were usually more in like chert instead of in limestone. Thousands of years later, that sediment fossilized, right? Breadcrumbs beneath my desk. Yeah, I think I have found fossilized breadcrumbs beneath my desk as well. So, and other fossilized microorganisms, yes. And so basically, what defines a biochemical sedimentary rock is, just as Noah said in the chat, is that you have fossilized microorganisms, or sometimes they're not microorganisms, they're larger organisms, you know, like what we're seeing here with the, this is kind of like a coconut. This might actually be more of a limestone. And I just want it to be coconut because I don't actually have a better one on hand. So let's go ahead and move on to another type of sedimentary rock. We're going to keep plugging along, trying to cram as much into lecture as we can today. We are going to talk about organic sedimentary rocks. These are very different from the other types of sedimentary rocks because now instead of taking a different rock or taking fossilized remains of an organism, now what we're doing is we're taking plant matter, organic material, right? Carbon-rich remains of once living organisms in terms of, like, specifically we're talking about plants, not organisms in terms of animals. Previously, we were talking about critters, critter shells. Now we're not talking about critter shells and bones. We're talking about like plant matter decaying. And there are a few types of organic sedimentary rocks. You can have like oil shale and coal, but we're just going to highlight coal for this class. So coal is made out of plant remains, right? So you have lignite, right, and bituminous coal. Let's see. Sorry. There's a couple of differentiations between lignite coal and bituminous coal. Essentially, there's this whole grade for coal. Coal originally starts as peat, plant material that's fallen into that swamp. Remember, I showed that picture in a previous slide of a swamp. Now, think swamp again, and we're thinking the leaves and bark and other plant material that falls into that swamp and gets preserved. And it first forms this like really weird organic material called peat, not like Pete, your friend Pete, but P-E-A-T, right? Peat. And then when that gets compacted, some more, it forms lignite coal. And that coal is usually a more brownish colored coal. It's a lower grade coal. It doesn't burn as nicely. And if you compact that some more, you're going to get another type of coal called bituminous coal. And if you compact bituminous coal further, it and expose it to even higher temperature and pressure, you're going to get an actually metamorphic form of coal. And we call that anthracite. And if you have the larger rock kit, the 50-piece one, there is actually a sample of anthracite. So now we're looking at metamorphic rocks here already. All right, your sample 22, I believe, is a anthracite. It's a metamorphic rock coal. So coal, sedimentary rock, but can also become a metamorphic rock if you put it through enough grief. So that's pretty much all that we're really going to say, though, about organic sedimentary rocks. We're just going to kind of talk about coal there and leave it at that, and we're just going to keep speeding right along into chemical sedimentary rocks. Remember earlier when I talked about like the precipitation of, say, like salt onto a branch or something, or so if you have like a really salty lake sea spray or something like that, or you have the Great Salt Lake, right? Depositing that liquid, that really salty water, deposits, it evaporates and leaves behind the salt crystals, perhaps just amassed together, right? Or perhaps onto a branch or something else that serves as like a nucleation point, something that the things form onto, right? Now we're talking chemical sedimentary rocks. So a nice definition that you guys can write down for that is minerals that crystallize directly from water. So out of a mineralized solution. There are certain types of limestones that are formed this way, specifically limestones like travertine and oolitic limestone. I believe you guys have a sample of travertine in your kits. It is sample number 23 for you guys. Let me pull out travertine. If you have the larger kit, that is sample number 28. Looks something like this. Really small. It's got this kind of like layered look to it. Right? Yours says tufa. Tufa. I'm pretty sure that's just another term for right. Tufa it's just another geology I love and hate you sometimes. It's calcium carbonate formed from the precipitation of water. Tufa and travertine, they're the same thing for our purposes. I'm sure that there is some subtle difference that if I look into my glossary of geology, which my laptop is propped up on right now. I raise up my laptop so you're not staring up my nose or something. The camera facing upwards, right? I'll show you briefly. It's one of the things I've stacked under my laptop. I'm sure if I look in the glossary of geology, this is a beautiful book. I love this book so much. Thank you, CWU. I got this from Central Washington University. I use it not too infrequently. I'm sure in here it would tell me that there's some subtle difference between tufa and travertine. But for us, it's going to be the same thing. So let me put this back underneath here. If you're a real big geology nerd like myself, I highly recommend getting your hands on a copy of the Glossary of Geology. This is another sample, though, of travertine right here. We can see this beautiful layering that we've got going on. It gets used a lot too in kitchens or on mantles. My mantle is actually made out of like little bits of travertine, kind of like a mosaic of travertine pieces. Rock gypsum as well as chemical chert instead of biochemical chert are also examples of chemical sedimentary rocks. Let's chat just briefly a tiny bit more about travertine. Slide 37 before I move on. Travertine is, it's basically an evaporite, meaning as all chemical sedimentary rocks are, it precipitates out of being dissolved in water. It precipitates out of that. Just like if you boil down salt water, you're eventually going to get a bunch of salt crystals left in your pan, and all the water will have evaporated away, and left behind the salt that was dissolved in the water in the pan. Same thing with travertine, except we're not dealing with salt here. We're talking about calcium carbonate. This can happen at hot springs. You find a lot of travertine deposits at hot springs. You also can find them in caves as well. Travertine forming in caves. And that's what those two pictures are there. The one in the center of the slide on 37 is a hot springs deposit. And then in the bottom right, those are travertine stalactites hanging off of the ceiling of a cave there. Let's move on to slide 38 and talk about chemical chert. So same thing, precipitating out of like a aqueous solution, except instead of calcium carbonate being dissolved in the water or salt dissolved in the water or something else, we're talking about silicon being like dissolved in there, right? So you get crystocrystalline quartz from this, right? And it precipitates out. However, also fitting into chemical chert is when you have that mineral-rich water that's laden with silicon in it. If it gets into an organic material and replaces that organic material, solidifies in its place. It basically like gives the organic material the boot and says, well, this is my home now. I'm going to take up residence here. And it ends up preserving, though, the original like shape and etc. of that organic material that it kicked out. You can get that chemical chert. And that's how you get things like petrified wood. So let's take a look at some petrified wood here. This is a beautiful slice of petrified wood that my husband gave me. We use it as a coaster. My other coasters are also rocks. They're agate slices and sandstone slices or granite samples from like those countertop stores, and they'll give you like a coaster size sample. And it's like, hey, this will make a great coaster. I have some other petrified wood. There it is that I wanted to show you guys too. All right. Looks like wood, doesn't it? I promise you, it's petrified. It's a rock. You know, even though these look like wood, I can convince you a little bit by going like this. You guys hear that? There's some dust in the air from doing that. Doesn't sound like wood though. Because it is quartz now. Same with this guy here, right? We'll do it to the edge because this is such a nice polished surface. Doesn't sound like wood. I'll show you these lovely pieces of petrified wood again. A student brought these in and said to a bunch of us others, you know, people on campus in the geology department as well as in the Mesa Club, they were like, help yourselves. I have more at home from my, you know, grandfather or someone who left them a ton of it. So, tink, tink, yep, that's the sound that they make. So otherwise that that chemical chert is going to really look the same as biochemical chert. I honestly am not sure if there's a way in hand sample to tell the two apart just by looking at it. But we do know that there are these different processes that form chert. And one of them involves the shells of siliceous plankton, the siliceous shells of plankton, right? And the other one involves quartz precipitating out of water that it is dissolved in, making one chemical and one biochemical. So let's go ahead and keep speeding right along to the next slide. Features of sedimentary rocks. And there you've got 3 photographs on that slide. Features of sedimentary rocks. Sedimentary rocks all not too uncommonly contain fossils, the fossilized remains of animals. There are different types of fossils. We won't cover them here in this class, at least I'm not planning to. If enough people in the chat though say like, please do a mini section on fossils, I want to know everything you know about fossils. If enough of you guys in there are like, please talk about this, do a mini section like on this. I might throw it in there, reorganize the class. I'd much rather talk about the things you guys are interested in geology than talk about the things that you aren't interested in, right? So you can get things like fossils, right? Some other sedimentary features that you can get are things like ripple marks. So the middle photograph on that slide, kind of out of those three there, are a bunch of fossilized, they are preserved ripple marks, ancient ripple marks from the bottom of a shoreline or a riverbank or something. Yeah, you can actually fossilize those. So I have a sample here that is either an example of soft sediment deformation or is a ripple mark. Difficult to tell from such, believe it or not, this is just kind of a small sample given the size of the feature itself, given the size of the sedimentary structure. But that might be an example of a fossilized ripple mark there. Could also be a fluke cast. You can also get preserved mud cracks. I have a sample here whose surface, I believe, may be also fossilized mud cracks. These almost look more like it could potentially be that blocky mudstone texture, right? But the side of it is like sandstone, so that's why I am leaning towards that surface actually being mud cracks. Potentially, I don't know for sure. We have some beautiful samples of ripple marks on campus. So the next time you're on main campus at Everett Community College, if you stop by my office or by the geology lab classroom, I would be happy to show you guys the outstanding ripple marks that we have. They're just really delicate, and I didn't want to transport them home and risk breaking those. We also should mention too, in terms of sedimentary structures, that sedimentary rocks also often form in these beds, these layers. And we call those strata, stratigraphy, study of, right? So this heavy rock is actually a limestone, but it oddly enough kind of really shows like this layering feature very nicely. It has this extraordinarily odd feature on the side here that almost looks like a bone or something, like a wishbone. Never found out what that was. If you know anybody who's really into sedimentary rocks and knows their stuff, let me know. I need an expert to tell me what that feature is there. Do you guys want to see some more fossils? Foliated. We'll talk about that word in the next section when we talk about metamorphic rocks. The word foliated we reserve for a metamorphic rock texture. Who wants to see fossils? I have some here. This guy I collected in Oregon. Nice little clamshell there. And I think I showed you guys, I know I showed you guys this earlier to talk about pearly luster. This is another little fossil ammonite there. Gigantic fossil ammonite here that a friend gifted to me when one of their loved ones passed away. This guy, I believe, is from Texas. All right. Fossil fishy. There's that guy. Found this one at a rock shop. I didn't find that one myself. Grew up fossil hunting. Always used to like them. Where did you grow up fossil hunting? Was it more in like Idaho area or somewhere in Washington? Let's see. This is from, these two fossil leaf samples are from Washington. There's another piece there. If you are interested, you can actually go to this location yourself. This is a stone rose fossil. Type it in the chat there. Shameless plug for this interpretive center. So Stone Rose Fossil Interpretive Center. I think I spelled Republic wrong. I totally spelled Republic wrong. It's okay though. They have this little interpretive center there that is kind of like a research field station / museum. Very tiny though, out of a house that's been converted into this center. And they own a plot of land in the town there, very tiny town. It's not a city, that is very prolific in searching for fossils. Let's see. Yes, my Echo. So did you grow up in Republic then? So Stone Rose Fossil, though, you can go there and pay, I think it's like $10, and you can keep 3 fossils that you find that day on their little plot of land. It takes a little bit of time. It definitely takes patience, combing over. And Noah says that he's been there too. That's awesome. But yeah, Stone Rose Fossil, super cool. If you go up there, it's in the northeastern corner of our state. It takes about 5 hours to drive there. Beautiful area, so gorgeous. Got to go slow and methodical when you're looking for fossils and you're looking for something that doesn't belong. So again, there's those guys. Stone Rose Fossil. And they do a lot of good research there. I love this one. This is a megalodon shark tooth. Megalodon sharks grew to be the size of like school buses. That's terrifying. So, all right, enough of looking at fossils. We could do this all day. If I had fossils for all day, I could do it with just the few that I have. Maybe not. All right, let's go ahead now and start talking. Oh yes, technically Curlew. Yeah, Curlew's right next to Stone Rose Fossil, I guess. I was talking with Noah, I believe, and Noah's told me that Curlew is right next to Stone Rose Fossil. All right. I'm trying to get a group of students interested in going back to Stone Rose Fossil as part of like a club trip. Like if anyone wants to get involved in MESA and go to Stone Rose Fossil as part of like a club activity where the college like pays for the trip, because our college is awesome and pays for club activities, hit me up. Hit up the MESA club. This is actually one last fossil. I don't know if you guys can see it. It's a leaf fossil. It looks like this guy could have come off of Blewett Pass. All right, enough of sedimentary rocks and fossils. Alrighty, so let's start talking about metamorphic rocks. Go ahead and check out slide 40. So basic observations about these 2 photos. There's 2 photos on slide 40. What are some similarities and differences that you guys see in those rocks? Definitely want to see several comments from you guys, from all y'alls who are tuned in right now. Oh, we've only got 6 people tuned in right now. Slide 37. Oh yeah, my slide has some hidden slides on your guys's. I apologize. My slide numbers have been off from you guys. Hopefully they were on up until that point. Yeah, slide 37. My apologies, guys. They've been off. So in slide 37, basic observations about the differences that you see in those 2 rocks. Yeah, slide 40 for you guys is a diagram. We'll get there. So go back to slide 37. My apologies. I'm so sorry, guys. And lines, no lines. Yep. In one, we're seeing kind of these lines, and we're not really seeing that in the other one. Pattern. What are some other similarities and differences you guys see? Anything and everything you guys see. Left sample grains, right side has wavy lines. You can kind of see some grains in the wavy line rock as well. But it's not like just this kind of spotted mix of various colors. The color is similar. The right side definitely has a higher concentration of dark minerals than it does light minerals, for sure. Colors, one is lined and the other is very speckled. Excellent observations. So keep these 2 rock samples in mind. We're going to come back to this in a bit. Anybody happen to know what the rock is in the top left corner? Go ahead and take a stab at it. I know you guys know. All right, there might be a delay in the chat, but it is kind of somewhere in between a granite and a diorite. I feel like if I squint, I might be seeing some potassium feldspars in there. And it's just ever so slightly got a higher concentration of light minerals than dark minerals. And we actually do have a name, because remember, these rocks kind of in the igneous rocks compositionally exist on a spectrum. It's not just granite, diorite, gabbro, and peridotite. There is this in-between transitional in between all of those compositions. And this one is nice and simply named granodiorite. Thank God it's easily named, until you start getting into more advanced geology, and then they really want you to characterize. Let's move on to the next slide for you guys. It is slide 38, similarities and differences. Observations, you got a couple pictures there. I'm a fan of the rock in the bottom right corner. If you guys are curious, since we won't be talking about that particular rock later, it is called an eclogite. I wish we had time to cover it, but we won't. We also, it's colloquially called the Christmas tree rock because it has a lot of green and red in it. The red are garnets and the green is, oh no, amphicite would be the blue. Chris Madsen, I hope you're not watching. Sorry, Dr. Madsen. It's some type of pyroxene, I believe, the green stuff. Can't remember which one. Sorry. Or amphibole. So the texture and crystals look different. The left side is more uniform than the right sample is more spotted, different colors, right? There's not actually hardly any similarities between this. I think that the one thing I could say that is similar to them is that there are some lighter minerals in both, and there are some more greenish kind of minerals in both. They're definitely different greens. Like the sample on the top left is it's like an olive green, very dark olive green. And then we have like a very bright grass green, Christmas tree green, Christmas colors green with the other one. So looking at these two slides, 37 and 38, what if I told you that in order to get the rock in the bottom right, you start with the rock in the top left and you expose it to heat, high temperatures and high pressures. And eventually, after that rock goes through enough of it, it will eventually turn into the other one. That is exactly the name of the game in metamorphism. I happened in these two slides to show you igneous rocks being transformed into a metamorphic rock. However, it's not always an igneous rock that gets transformed into a metamorphic rock. You can start with literally any rock. You can start with limestone or like petrified wood, or you can start with sandstone or an igneous rock, or you can even start with a metamorphic rock and then subject it to plenty of torture in the form of high temperature and pressure, and then transform that rock. So the next slide there, slide 39, is really just because I love showing people the scale of geology. I think that's one of the more captivating things to me to geology. What you're looking at there is a very large mountain outcrop of metamorphic rock. Looks an awful lot like the rock that we were taking a peek at on slide 37, except it's got some more brown iron oxide on the surface there. There's actually a person in this photo for scale. So if you look really closely towards the center of the picture, there's a snow line there. And then there is actually a guy standing right next to the wall. He's like this little tiny dot. Let me know if you found the guy. Oh, I see that there is a hand raised in the chat. Miss Alicia asks, how long does the process usually take? I think it really depends. I think it depends on how hot your temperatures are. It depends on how high the pressures are. And you're going to get different types of rocks. I'm not sure that there is one set period of time that it takes, right? But more than like a day. More than a day. We'll go with that. So it varies for sure. I'm not really sure what the average, if there's like an average, or what the spectrum even is. I take it back. Hydrothermal alteration can probably happen fairly quickly, actually. And we'll talk a little bit about that on the next slide, slide 40. The hydrothermal, is kind of that last bullet point on there where it says chemically active fluid. But let's start from the beginning and let's talk about the agents of metamorphism. So let's talk about heat, pressure, and fluids, right? Water and things. So heat is the most important driver for metamorphism. It's the main catalyst. It's the most important catalyst. Why? Because that is what triggers chemical reactions to occur in these rocks. Again, we're not melting them down completely. However, we don't need to melt it down completely in order to still have these chemical reactions take place and to transform the minerals in the rock into another type of mineral. That's what we were looking at on the second slide that I had you guys make some basic observations up, where we were looking at the gabbro sample being transformed eventually into eclogite, right? We don't need to melt that rock down to transform those minerals. We do need a lot of heat to trigger that chemical reaction, though. So The next kind of important agents of metamorphism is pressure. And we're kind of going to break that down into confining pressure. What is confining pressure? Confining pressure is when you squeeze an object and you apply pressure to the object, equal amounts of pressure to the object in all directions, right? So every single surface of this rock, I'm doing my best to squeeze evenly on all the surfaces, the same amount of force and pressure evenly. Differential stress, another form of pressure, or at least falls into the category of when I say pressure. Differential stress is when you have unequal pressure in different directions. So for example, if I take this rock and instead of kind of cupping it in between my hands, I squish it in between my hands this way. Now I am applying only pressure on this surface and this surface and not on these surfaces, right? So it's unequal pressure and it's in different directions. You can also apply different amounts of pressure in different directions. So I can be pushing really hard this way, and maybe I could have someone else come alongside and just give like a little bit of pressure that way, right? And then you can get things like shearing and whatnot in your pressure, where not only do you squeeze down on the rock, but you also like push in one direction and in the other direction as you apply that pressure. And that's really important for forming some of these metamorphic rocks, right? So an example, let's go with this one. I love this rock. What rock do I not love? That's a good question. So here we can see this line quite squiggly through this rock. There it is on the other side too. And this is because we applied pressure on this rock. These lines going this direction were not really affected. Why? Because they are this direction in the rock. And this one here was kind of more this way originally. And then it got squished and compacted, and this one got all messed up, got all squiggly like. Let's take a look at another cool feature. Gosh, this rock is heavy. That one came from Idaho, near Mackay, Idaho. And this one here came from over by Lake Chelan. So does anyone notice some interesting features on this rock? What do you guys see? What I want you guys to see, there's lots of things to see. What I want you guys to see is this red dot here. And then there's like some tapering white on either side of that kind of reddish colored dot. That reddish colored dot is a garnet. And then we've got some kind of quartz on either side. Those are strain shadows from pressure and stress and strain going on in the rock. You guys can look up more on that. We're definitely getting into geology like 201 if we start talking too much about how oggons are formed. But yeah, you get these really interesting features as a result. Sometimes you don't get interesting features. Sometimes you really can't tell. Foliated versus non-foliated. More on that in a few slides. Anything else? Yeah, let's talk about chemically active fluid, aka hydrothermal alteration. That's how I prefer to say it. I believe that your book, though, calls it chemically active fluid. What this means is you have that water that's got those dissolved minerals in it, but with the added condition now that it's really, really hot. Hot water with dissolved fluids in it. And when you run that alongside and through the cracks in the ground that are also extremely hot as well. You can change the arrangement and shape of existing crystals in that rock, especially if you're running it through and along like the crystal grain boundaries and whatnot. And you can also change the chemical composition because that hydrothermal fluid can grab some of the elements that are in that mineral and take it with it and leave some other behind, right? So you can change the arrangement and shape of existing crystals, and you can change the chemical composition even of existing crystals. And that's the kind of third way that we can transform a rock, the third kind of agent of metamorphism, as we'll call it for this class. So let's go ahead and look at that next slide there. I actually left the text on this one for y'all. So just kind of in summary of the previous slides, change metamorphism, new rocks from old. What we're doing is we're changing the mineralogy. In most cases, we're changing the texture of the rock. And we can also sometimes change the chemical composition even. Chemically, what we started with is chemically not where we end up. Parent rock is going to be an extraordinarily important term moving forward. Parent rock means the rock that you started with. Whether you're starting with a limestone, starting with a sandstone, maybe you're starting with, say, hold on, bear with me. Maybe you're starting with a granite, or you're starting with, ouch. You're starting maybe even with a metamorphic rock. This one is schist. Look at the little pretty baby tiny petite garnets in this guy. Hope you guys can see that. Probably not. Let me take a look at the viewer. I've had YouTube just in the background. Can you guys see the little dark dots on there? They're little baby garnets. This guy came up by Leavenworth. You can find samples just like this along Icicle Creek Road. That's where I found this guy. And the garnets there, while they're small, they're really nice and euhedral. Like their crystal shape is just perfect. They're not like messed up. They're really euhedral in shape despite being small. So parent rock is the rock that you start with before you subject it to heat, pressure, hydrothermal fluids. It's just what you started with before you buried it and subjected it to high amounts of pressure and temperature and potentially hydrothermal fluids. So, and your parent rock, it could be an igneous rock, it could be a sedimentary rock or a metamorphic rock. There's a lot of really interesting research on overprinting of metamorphic rocks where you have like a metamorphic texture from the parent rock that you started with, and then you metamorphose it again and recycle it again, and then you get like an overprinted new texture like on top of the previous texture. Metamorphic overprinting. Another thing you guys can research in your spare time during quarantine. If you're really into it. So let's talk about two different types of metamorphism. We've talked about how metamorphism takes place. Now let's talk about two different kinds of metamorphism, two different ways that these processes that we just talked about happen. You can have contact metamorphism, or you can have regional metamorphism. And so what you're looking at there next to the contact metamorphism is you're seeing like a magma chamber, an area of that's very, very hot. You've got that hot molten rock, right? And it's in contact with rock that isn't quite melted, right? And in that area right next to on the boundary where you have liquid rock versus not liquid rock, you have this immense heat in these rocks, and that becomes the source for all of these agents, right, for the heat and whatnot that's going to going to transform those rocks. So contact metamorphism, you can think of it as like putting a pan on a hot stove. It's because the pan is in contact with something that's really, really hot that serves as the catalyst for the metamorphism to take place. So heat conducted into the rock from an igneous source is typically how you get contact metamorphism, and it's what we'll cover in this class in terms of contact metamorphism. Regional metamorphism, however, takes place over an extraordinarily broad region. And when I say region, I mean an expanse of land, like a mountain range, kind of regional, like an entire mountain range. So it usually regional metamorphism takes place over a broad region, usually the result of burial, right? And after burial, then compression, because when you bury something, you're also adding weight to the top of it. So burial and compression during like mountain building type processes. And you can kind of see that taking place in that block diagram where you start with strata that looks, ooh, this heavy guy, that looks like this, right? And then you squish it, you make it really, really hot and pliable, and you squish it. Solid rock, by the way, can be, under the right circumstances, it deforms like fluidly kind of, or plastically, we would call it. Oh, let's set that guy down. Oh, so heavy. Can you hear that thud when I set it down? Let's also talk about metamorphic grade. So on to the next slide there. Metamorphic grade, what does this mean? Did it get an A or a B or a C? No. What we're talking about here is how much pressure and how much temperature did it get exposed to, right? So the higher pressure and the higher temperature that a rock is exposed to, the higher the metamorphic grade. We're going to transform that rock more and more if we expose it to higher temperatures and higher pressures. This diagram that's on here on, let's see, the slide number for you guys is slide 43. So what you're looking at there is seeing some rocks fall into the category of not a lot of temperature exposure and not a lot of pressure exposure. And you get a low-grade metamorphic rock. One such example is shale. Let's see, do I have an example of shale here with me? I do. There it is. Looks a lot like slate. Or excuse me. Slate is the metamorphic rock. Shale is the sedimentary rock that we talked about before. You guys have a sample of shale, right? Shale and slate. Always have trouble keeping the names straight. I hope you guys can hear this, but there is a difference in sound between like shale, which is a sedimentary rock, and slate, right? Do you guys hear the difference? I wish I had a harder table instead of this plastic table that I've got here. They basically, one of them sounds like a lot more metallic-y normally if you put it against a table that's not plastic. And also slate is a lot shinier. Shale has a really kind of dull luster to it, dull texture, not very shiny. Slate, on the other hand, you can see that it's reflecting a bit more light than the other one. And it's even more like layered. It's even more fissile is the word for that. It's probably not in your book, that word, but we're going to use it because it's an effective term. So hopefully you guys can kind of see the difference between these two, right? So basically when you expose shale to really low temperature and really low pressure metamorphism, relatively speaking, you're going to get this rock here, slate. We used to use it for chalkboards. We still do. If you have like a chalkboard that's like a rock, it's probably slate. Getting dust everywhere. IT, I promise I'll clean this laptop before I give it back to you. However, if I continue to put this rock through it, I'm eventually going to get something like schist. And then if I keep, exposing it to even higher temperatures and higher pressures, I might get something like gneiss out of it. Gneiss. And if I expose that yet further, I might get something like migmatite. I have a migmatite. I think it's in a box though. Sorry, guys. We won't talk about migmatite beyond that. So metamorphic grade, how much temperature and how much pressure. So some rocks can be exposed to really high temperatures, but not a lot of pressure. And you're going to get a certain type of rock like hornfels because of that. Or you can expose something to really low temperature, but a lot of pressure, and you're going to get a rock called blue schist out of that. That's what that diagram is showing, is the different places, the different kinds of rock that you're going to get as a result of how much temperature or how much pressure you're exposing the rock to. Let's go ahead and keep chugging along. Hang in here with me, guys. We'll probably go for a bit longer. As you guys can see, there are more slides. It's such a hard lecture to squeeze down into one. I normally do this over 3 weeks. Let's go ahead and talk about foliation. So that's a term that we mentioned earlier that Noah mentioned. We reserve this term for metamorphic rocks. Foliation is when you can kind of see like a pattern in the metamorphic rock, or not on, and that pattern being like physical or visual. So this rock here, the slate, is foliated. You're not really seeing like coloring foliation going on here, but you can tell that it is like it's got this distinct, physical layering going on in it. Whereas if I show you this rock here, this one's not the best one. Give me a second. Hopefully the light reflects really well on this one. So hopefully you can see that there are a bunch of crystal grains that make up this rock. They're all the same color though. You can see different surfaces of different crystals shining back at you. But it's all random. They're not all like look squished in the same direction. And there's not like banding in the rock. Whereas with this rock, you can see that it's what we would say oriented, right? In a certain way, causing that really fissile breaking off into sheets kind of type of thing going on. Foliation, I'm going to give you guys just kind of a quick, good definition for this. Foliation, it's the development of a flat arrangement of mineral grains or structural features. So if you look at the diagram there in the top right, what you can see is you're starting with that's supposed to be a rock, and that's kind of circled there. And you see that there are these elongated black minerals in it, and they're kind of facing every which way. And it's just a bunch of chaos. Whereas if you expose it to metamorphism and certain pressures, and you foliate this rock, if this rock is going to have foliation, you'll align those elongated minerals, right? And then right below it, you see an example of a rock. In this case, it's an igneous rock where you have these dark grains. They're not even really very elongated in that particular sample. And then you squish it, right? And you squeeze the grains. And not only that, but not only have you like thinned them out and made them elongate, but you've also oriented them all to be kind of facing the same way. And that's happening just on a level that you can't really see with your naked eye, and also because there's not a lot of color differentiation in this rock, and that's why it's breaking into those thin sheets. However, you don't always get thin sheet breaking off like in the example of gneiss. The slide, the really colorful slide in the bottom left corner there, can you guys kind of see how there's like a wave to that rock? That's actually a rock. It is underneath a microscope though, and we've put some filters on it to help us see the different minerals that are in that rock and help us be able to identify those minerals. But that actually is a rock, and it does have a wave to it. Let me show you a rock that has that kind of wavy texture to it. This metamorphic rock right here. So this is not slate. This is the next step in metamorphism. It kind of looks like a clamshell, doesn't it? It's all wavy like. This is the next step. This is phyllite. And this is foliated. Foliation it's a challenging thing. Spend some time at home on foliation. You can see some waviness in this rock too. It's a lot easier to see it in person, but the surface of this rock is kind of wrinkly. Can you guys see how it looks a little wrinkled on that surface? It's not completely smooth. Mostly smooth, just with wrinkles in it. So that would be an example of foliation. So go ahead and go to that next slide there. For you guys, it is slide 45. Checking out how those rocks at the top 4 are examples of foliated rocks, and they show kind of a sketch of the texture. You can see like in the first one, you've got those platy minerals that are aligned in the slate. And then in the phyllite, you have that, we call it crenulated, wavy texture going on. And all the grains are kind of aligned. And then in schist, the grains, the crystal grains in there of the minerals are a bit larger. And they're not as flat, but they are somewhat elongated, and they're all facing relatively the same direction. And then in gneiss, not only do we have grains that are kind of elongated, and they're pretty coarse grains, they're a lot larger grains. They're not just like thin lines by comparison, at least drawn by sketch, right? Not only do you have that, you also have the lighter minerals and the darker minerals segregated from one another. And that would be this guy. And that's another type of foliation, right? I love this rock. Kind of like wrinkled foil. Yeah, kind of like wrinkled foil indeed for the phyllite and that kind of crenulated, wrinkly, wavy thing. So here we can see the light and dark minerals are separated out from one another into these kind of bands. And I have, let's see, let's go ahead and do we have time to talk about, let's go ahead and do it. Let's do a crash course. I mean, technically I have y'all for 3 hours. It's not a crime if we go over my target time. I try to make these lectures shorter for you guys to make them just a bit more digestible, but we do what we can in the time that we are given. So let's go ahead and talk about, we've already talked quite a bit about slate, so definitely not going to spend a lot of time here talking about specific rocks now. Slate, its parent rock is a mudstone shale, breaks into those sheets, right? It kind of has a silky, shiny way of reflecting light, looks kind of silky or shiny. And another way you can identify it is that it makes a really hard tapping sound when you tap it against like a hard surface. And they often slate gets used for like an architectural stone, whether that's like flooring or a facade. People also use it for chalkboards, right? Or for cheese boards. I have a cheese board that is made out of slate. I forgot to grab it, but whatever. There's a picture of one for y'all. I love fancy cheese. Love connoisseur's cheese. Let's keep moving along and talk about phyllite. So both of these are samples of phyllite here, right? Where you have that kind of wrinkly wavy. The parent rock for this is also mudstone, shale, or slate, just like with the slate stone. You also have mudstone and shale. However, you can take a slate and make a phyllite out of that as well. You've got that wrinkly wavy. It also looks silky and shiny, but even more so than slate does. And sometimes it even has a metallic luster to it. And you can see that on the slide. What slide number is that for you guys? Slide 47, looking at phyllite there. There's a thin section picture there so that you guys can kind of see if you do present on that and you click present, you'll see this really like pink thin section microscope view of the rock, and you can see that all the grains are kind of like oriented a certain way, right? Likewise with the bottom thin section photo that is black and white, you can see a little bit of the waviness in it too. And this also gets used as, I can't remember what that stuff is called, but kind of like plaster. An economic use of that mineral or of that rock. They grind it down and use it there. So foliated metamorphic rock. Let's keep going to the next slide. Just keep going along. Schist. So the parent rock for schist, again, it could be mudstone or shale. And not only that, you can take the rock we just looked at, phyllite or slate, and also make schist out of that. There's a really beautiful rainbow kind of looking thin section there, and you can see how things are kind of oriented right into this pattern diagonally. Call that a fabric. I actually took that picture of a schist under the microscope. So I really like that picture. Thought it was very aesthetically pleasing when I came across it under the microscope. So here I have an example of schist for you guys. This is a very classic example. What makes this such a classic example is that it is very shiny, very reflective. And not only that, but I wish I could hand it to you guys because you would see that it's made out of, the minerals have been transformed into very flaky mica family minerals such as muscovite and biotite. And it's primarily made up out of that. I'm even getting like flakes like on my laptop as I do that. So the rock I showed you guys right here from Leavenworth along Icicle Creek is also a schist. No, I'm not saying a bad word. The rock is called schist. But this is a really fine-grained schist. All right. So sparky, flakily minerals, and maybe even other minerals such as those garnets, right? Or sometimes you can get some other gemstone minerals in there like corundum or emeralds, beryl. So corundum or beryl and other beautiful gemstones. Moving right along to the next slide, let's talk about the metamorphic rock gneiss. So the parent rock for that again, are you guys seeing a trend here? Mudstone, shale, slate, phyllite, or schist. If you go back to that diagram that we looked at before I started talking about individual rocks as well as foliation, if you go back to your slide 43, you'll notice that same progression on the metamorphic grade. I've basically been increasing the metamorphic grade as I talk to you about these different metamorphic rocks. So going back to slide 49, talking about gneiss, the parent rock again, we just went over that. Light and dark bands characterize this rock, where you segregate the what are considered lighter minerals, the more silica and feldspar type minerals, from the darker minerals that are more iron and magnesium rich, right? So we've got two kind of examples of gneiss there, where one of them's kind of more pinky, one of them's just black and white. There's a beautiful countertop in there that I wish I had in my house, as well as a thin section slice there where you can kind of see that banding going on under the microscope. So, chugging right along, we just covered in all of those rocks that I talked about, some of the really big key foliated rocks where you can see orientation, right? Of mineral grains and banding and whatnot, and these textures, right? So now we're going to chat about non-foliated metamorphic rocks. Also, you guys do have samples of some of these in your kits. So you guys do have a sample of gneiss in your kit, sample number 16. Go ahead and take a moment to look at that. So and you also do have an example of schist in your kits. It's probably not very good. It's probably really fine grained, but you can see that it's got these really sparkly, platy minerals that are fairly well cemented together in your sample. And the Icicle Creek rock schist was also fairly well cemented together, as opposed to this guy, which is just not, it's a little bit less consolidated. So go ahead and take a look at those really quick. And then we're going to move on to the next slide, which is about, we're beginning to now cover non-foliated metamorphic rocks where you can't see those fabrics whatsoever. I know the next slide after this kind of tricks you into thinking you're seeing a fabric, but it's not a fabric, I promise. Anyways, anthracite coal. We mentioned this briefly, kind of gave you some spoiler alerts to it, where if you expose bituminous coal to more temperature and pressure, you're eventually going to get it into metamorphic territory and form a really shiny form of coal that is called anthracite coal. And it is just way shinier than regular coal. I actually have some regular coal here to show you guys. Forgot to show it to you earlier. Oops. Come back to the YouTube screen there. So this is pretty shiny. This is bituminous coal. This is shinier. This is the metamorphic anthracite coal. Can you guys see how this one is slightly duller than this one here in my left hand? Big chunk of coal. I actually opened 3 boxes when I was going through the college's collection. I think I got rocks specks in my tea. It's okay. It wouldn't be the first time I ingested rocks due to being a geologist. That's a shame. This tea is really good. Plug for tea. Harney and Sons, Yin Hao Jasmine. So good. Anyways, I found 3 boxes, big boxes, and in them was nothing but coal. And not only that, but this is a small chunk compared to what was in there. They were like really big, like the size of my head, chunks of coal. I was like, why do we have all this? We have all this because someone donated it. I got rid of some of it. We just don't have the real estate to keep storing it all. They took down Index Hall. That's where we were storing most of it. They took away my storage space. There was much wailing and gnashing of teeth that day. So let's go ahead and, oh yeah, by the way, this coal produces a lot more energy when you burn it versus this coal. That's the last thing I want to say about coal, other than if you look at them, you can see no fabric to these rocks. You can see no foliation to them, right? It's just a mass of rock. All right, let's go ahead and look at the next slide. We're going to talk about serpentinite. The parent rock, did I talk about, well, the parent rock for coal is obviously coal. The parent rock for serpentinite is going to be stuff like basalt. Remember that igneous rock I moved the igneous rocks. We looked at the parent rock basalt on Monday, as well as gabbro. You can also take a peridotite, right, and turn that into serpentinite after exposing it to a lot of temperature and pressure. The primary mineral in serpentinite is, imagine that, serpentine. Serpentine is like, oftentimes has kind of a platey like structure to it. And that's what you're seeing in the thin section slide that I took, photograph that I took there. I took that photograph too. I love it. But in any case, this rock usually, it's not foliated though in sample. I didn't bring a sample of serpentinite with me. They're gorgeous, and we have some very beautiful ones on campus if you're interested in ever seeing them. They're too heavy to bring with me. They are so heavy. Very dense. These also get used a lot in architecture. Take some time later to blow up those images there of the stone facade. It's this gorgeous green with kind of these white quartz lines in it, as well as the countertop also depicted on that slide. Just beautiful stone, gorgeous architectural stone. Let's talk about the next slide. Soapstone. You have a sample of this in your kits. I had you guys use it as the sample talc last week for looking at minerals. Soapstone is overwhelmingly composed of talc. However, there are a few other things in there that make it a rock versus just a straight up mineral. But it's so overwhelmingly talc that you guys could test it as as just the mineral talc. The parent rock for soapstone is surprisingly also usually a basalt or a gabbro or a peridotite, just like with serpentinite. However, it's exposed to different temperatures and pressures that cause one rock to result, serpentinite versus soapstone. And soapstone is also often used in carvings. For centuries, they've carved it, especially in a lot of like Asian countries. I have a really beautiful soapstone carving here that I bought at a rock show. There's also like a base to this. Soapstone isn't always a light color. The base to this that this guy sits and stands in is like this dark brown color. And I originally thought it was wood until I like touched it. And I was like, oh, this has like a waxy feel and I can scratch it with my fingernail. That is also talc. So it's so soft, again, softer than your fingernail even. And you can make these just stunning carvings out of it. People have made like intricate like buildings and put like people inside the building carvings out of soapstone. So let's keep plugging right along. Moving on to some more non-foliated rocks where you just can't see any texture going on in it. Let's talk about marble. Parent rock for marble is limestone. So limestone, we talked about this, kind of fizzes with this stuff because it's primarily calcium carbonate. Well, so is marble. And marble, again, another very famous architectural stone, gets used in a lot of monuments or in a lot of buildings. However, it is really weak compared to acids because it's calcium carbonate, and that stuff isn't very stable and dissolves quite readily in the presence of acids. And that's why they actually close down a lot of these monuments, not too infrequently, to refurbish them, right, and to repair them, because rain is usually slightly acidic, and it actually over time deteriorates all of these monuments and things like the Parthenon and whatnot, and they have to go back in and kind of touch it up a bit over time. Again, non-foliated. You can't really see any pattern going on in here, and when it breaks, it just kind of breaks at random. What you're looking at there too in the bottom right is some gold veins in that marble. So it is a coarse-grained rock, typically light in color, and the only way to distinguish it in hand sample, not the only way, if you're really good at what you do, you can probably tell the difference, but sometimes the next slide, the next rock that we're going to talk about, is also sometimes quite coarse-grained, and it's really useful to have a bottle of hydrochloric acid to test and tell the difference in hand sample between quartzite and marble. So let's talk about that last and final slide. We did it, guys. Finally made it to the end. I appreciate those of you who stuck with me. I think almost all of you stuck with me, who were here from the start. Quartzite, the last one. The parent rock for this is going to be that sandstone, typically, right? And it's a coarse-grained rock. There is a bit of a textural difference if you look at the previous slide rocks to this slide. Another, of course, architectural stone. Oh, by the way, here's another marble. It's kind of a more traditional marble that you guys are used to seeing. I don't have a sample of quartzite on hand. Nope, but that's okay. It looks just like the pictures that you're seeing there. Yeah, parent rock sandstone, and it's coarse-grained and usually lighter in color. Sometimes it's got those darker grays, but still fairly light in color. It's not super dark. Yeah, and that concludes talking about metamorphic rocks. We did it, guys. We made it. We made it. Triumph. Okay. With that being said, before I let you guys go, there is one other thing that I really want you guys to pay attention to in your textbook that we didn't cover Monday in lecture due to time constraints, but I really want you guys to go over it in your books. I have to unbury my book from rock samples. Bear with me while I turn to the page that I want you guys to read on and study up on. All right, so in your book, Foundations of Earth Science, there's really a couple. So looking at this diagram here on page 49, this is going to tell you what minerals you find, just like those previous slides, in the different igneous rocks. So that's going to be your friend working on this lab. And then, moving several pages over, we did not talk about the extraordinarily important Bowen's reaction series in lecture. And that's this chart here on page 55, at the top of page 55. This is incredibly important. It talks about what minerals are going to crystallize and solidify first out of molten rock. So you're going to start with these more mafic minerals and work your way into those lighter minerals and start making things like granites and rhyolites kind of late in the game. So a magma that gives you a granite or a rhyolite is kind of, I like to think of it as a very matured magma or lava. there's it's had other things precipitate out of it along the way and form out of it along the way. So read up on Bowen's reactions series. I believe that I've given you guys the foundation though to understand it during lecture, but please let me know if you have questions on it. Also, we need to chat about the test. I'll make an announcement for what I did decide, make a decision on what I want to do for the exam. What I'm going to have you guys do is take the exam on Monday at 3 o'clock during class time. I just saw the comment that quartzite reminds Alicia of beef for some reason. I also have a rock that's not quartzite, but it literally looks like a steak. Anyways, ADD tangent there. Let's talk about the test. You can expect to see some multiple choice questions. You can expect to see some visual questions where I'll give you a picture and I will ask you questions about that rock. It might not be a rock. Sometimes they're just like a picture of various things related to like plate tectonics or minerals or stuff. And I'll ask you questions about those pictures. And some of them will be kind of short answer questions for Monday's lecture, because we still have material that we'll need to go over on Monday. I think what I'm going to do for that is probably move that to Tuesday at the same time, Tuesday at 3 o'clock. I understand that most of you guys, some of you guys may not be able to make it on Tuesday to the live lecture. So that's totally fine. If you can't make it to the live lecture, join us if you can. You are stuck at home, hopefully, unless you're an essential worker. Thank you to those of you who are essential workers again. Let's see, anything else I should mention about that? It is a timed test. Know your stuff. You're probably, thinking I'm going to give you guys like maybe an hour to an hour and a half on the test, depending on how long the test I make the test to be. Might be closer to an hour. And it will start for everyone at 3 o'clock. Yeah, let me know if you guys have further questions. I got your plate tectonics labs graded, and I'm hoping to have your focus questions and minerals lab and your, both sets of focus questions graded by Friday, if I can swing it, right? Because I have that other job where I have other instructors asking me to do stuff for their classes too. I work 2 jobs on campus. It's fun. And that's it for today. So I hope you guys have a great rest of the week. Let me know if you have questions about anything. Remember though that I typically only check my email between the hours of 9:30 and about 5 p.m. Sometimes 6 p.m. And I usually only check it Monday through Friday and not on the weekends. So if you have a question or you want to set up like a Zoom meeting, be sure to get to me by like tomorrow evening to let me know that on Friday you want to set up like a Zoom meeting or something like that. And if you email me on like Friday evening, I won't probably see it until Monday morning. So just keep that in mind. But yeah, if anyone would like to do a Zoom meeting after this, starting now, not a Zoom meeting, but I really do have a preference for Google Hangouts. If anyone would like to do a Google Hangout session, let me know, send me an email, and we'll get that set up. Have a great week and study up for the test. So enjoy your weekend too, Alicia. All right, I'll probably give you guys just like probably give it like another minute or two, since I know that there's a delay in the chat, in case anyone wants to have that like Google Hangout session afterwards. My rock-filled tea. I think most of the rocks chips settled to the bottom. Oh no, not that piece of muscovite biotite. There we go, got it. The things geologists do. You're welcome, Genesis. Have a good one. All right, I don't see haven't seen any requests in the chat for a Google Hangout session, so I'm gonna sign off for now. Thanks for sticking with me this whole time. Cheers to you guys, and I will have another next live lecture is going to be on Tuesday at 3, and the exam is going to be Monday at 3. So be sure to have your reliable internet connection all set up, ready to go on Monday. So, all right, have a great weekend. Have a great rest of the week, everybody. Bye.